Bonjour à tous pour ce dernier séminaire du GDR de l'année académique. Comme je vous le rappelle, on essaye de faire des GDR tous les mois sur tous les aspects, donc formels et algorithmiques de l'intelligence artificielle, qui se veulent assez ouverts pour que toute la communauté puisse comprendre le contenu des présentations, ou au moins une bonne partie de ce contenu. Et donc, aujourd'hui, on reçoit Dominik Peters, qui va bientôt rejoindre le LAMSAD en tant qu'agent CNRS. Et donc, c'est une proposition du GT jeu. Donc, je vous rappelle que chaque groupe de travail peut très bien proposer les gens qui interviennent mensuellement, ou sinon le comité de direction du GDR en proposera. Et donc, je vous rappelle qu'on enregistre le séminaire, on réserve les questions plutôt pour la fin, donc on n'enregistre que la partie présentation, on coupe les questions. Donc, ce sera disponible plus tard. Et donc là, je vais tout de suite… alors, le prochain séminaire en septembre, normalement, pour ceux qui sont là, ça devrait être Didier Dubois, mais on n'a pas encore de date ni de titre. Donc on vous donne rendez-vous aussi vite que possible pour vous donner les infos. Et je vais tout de suite, vu que Christophe Ray n'a pas pu être là aujourd'hui, je vais tout de suite passer la main à Stefano, qui a donc accepté de participer, enfin d'animer scientifiquement le séminaire. Et sinon, il y avait une remarque de Christophe que ce séminaire, c'était aussi éventuellement le moment pour mentionner le fait qu'il y a peut-être un GT sur le choix social. Donc, je ne sais pas ce que Sébastien en pense, il pourra nous dire quelque chose là-dessus après le séminaire. Serait peut-être intéressant. Donc voilà, et là, je te laisse, Stefano, je te laisse la main pour présenter Dominique plus en détail et gérer l'ensemble de la session.
Merci Sébastien. Oui, moi aussi je pense que ce serait une très bonne idée de faire un working group en computational social choice. I switch to English, so perhaps I can speak also with Dominik about this structure that maybe is new for him, about working groups. First, research groups and then working groups like the one in algorithmic game theory and algorithmic decision theory that we have within the group of research in artificial intelligence, and that is also aimed at studying aspect of computational social choice. So I guess that there are also many other projects, ANR projects related to computational social choice, like past and the present, like Cocorico or Themis, Amand before them. And so I think that would be a very good idea to create a new working group, even if I guess it already exists. There are many people working on this very interesting domain. So there are many groups that gravitate around the domain of computational social. As far as I know, there is no groups with this name, and I think that it would be very nice to have such a group within the research group in artificial intelligence. And this is also the opportunity, this seminar to say once again that would be very nice. Anyway, today it is my greatest pleasure to introduce the seminar of Dominik. Those who know already the research of Dominik are well aware that he did a very important contribution in many fields like computational social choice, voting theory, game theory, preference aggregation, design of fair algorithms, and many other fields. For those that do not know yet Dominik, but will have the opportunity very soon to meet him in Paris at LAMSAD, it suffices to have a look at his impressive CV. He was previously postdoctoral at Harvard University with Ariel Procaccia, and also he was a PhD student. He did his PhD as the Department of Computer Science in Oxford, just to cite some with Edith Elkin. And he has an impressive list of distinction and awards. Just to mention one that is really impressive is the prestigious Victor Lester Distinguished Dissertation Award that he received during AMAS 2020. So we are very happy to have today Dominik for the seminar, and I'm really pleased to give you the floor to introduce this seminar about participatory budget. So thank you, Dominik.
Thank you very much. That was an extremely kind introduction. Yes, so I've also made a slide about my CV. So I'm originally from Hamburg, did my PhD in England, then some postdocs in America. Now I just recently moved to Canada, where I'll spend a few months until next February, when I'll move to Paris. And as you can imagine, I've been busy trying to learn French. It's not going all that well. I had it for 5 years in school, but I forgot everything. So let's hope that in February or a bit later, I'll be able to understand at least some basics. Okay, so in today's talk, what I'm going to talk about is, in general, fairness in decision making. So I'll start with a quick overview of different types of fairness that have been studied in artificial intelligence in various subcommunities. Then I'm going to introduce participatory budgeting, if you don't know what it is. And I'm going to argue that the standard way it's usually done is bad. So participatory budgeting is used by cities where they let the residents of the city vote over how the city budget is going to be spent. And the voting rule that's commonly used is a very simple one, like sort of a greedy knapsack method, and that ignores minorities in a pretty bad way. And so I will want to design better voting rules that are fairer and take everyone into account. So how to do this is actually a pretty difficult task. And so I'm going to draw a connection to multi-winner voting rules. These are voting rules that are designed for electing parliaments. And that's actually a special case of participatory budgeting. So the hope would be that we can then lift rules from that domain up to participatory budgeting. And then I'm going to also briefly talk about an impossibility theorem for these voting rules that I've obtained using SAT solvers, which is a cool technique. Okay, so let's talk about fairness in general, which of course, fairness is a very vague term, and so everyone can use it for their own goals. A growing field is fairness in machine learning, by which usually is meant fairness in classification. So the setup is that the agents are partitioned by features. So each agent, we look at them as a given feature vector, and that might be like gender and race and income, things like this. And these are protected characteristics, and we want these characteristics to not influence the classification process unduly. So usually the goal would be that the classification accuracy is the same for every type. And so this is typically studied in domains like credit scores and such like, or which ads to show which people. And there are like a whole bunch of fairness notions for that. There's like a paper that's talking about 21 different fairness notions, what it means to have the same accuracy for every type, and they are all pairwise in conflict with each other. Right. So this is one fairness notion, and one important part of it is that it's fairness with respect to these given features of agents. And I'm not particularly interested in that kind of fairness. I want to be fair to agents, and looking them at black boxes, the thing I'm interested in is their preferences. So I want to satisfy their preferences, and maybe I want to treat agents with different preferences fairly, but it's not just a given partition that is supposed to be the right one. I want to sort of treat everyone simultaneously as fairly as possible. Another notion of fairness is in resource allocation. Suppose we have a bunch of items that we need to give to agents. And then the aim is that every agent should receive a fair amount of the items, and no agent should envy another. So no agent should get nothing, for example, if possible. And also among no agent should think another agent got a better deal than them if we can avoid it. And so my two postdoc hosts actually have built this website called splitted.org, where they've implemented various fair division algorithms. So for example, if you're moving into a house with your friends and you have several bedrooms and you need to split the rent among all the housemates, then you can do it with this app where everyone puts in how much they like different rooms. And then based on that, they compute an optimal matching of rooms to people and a way to split the rent so that no one would like to have a different room with their rent. So the fairness notion here is no envy. No one wants to move rooms. And then the type of fairness that I'm going to talk about now is, generally speaking, fairness in public decision making. So suppose we need to make one decision together, and what we do will impact everyone. So how do we do it? Well, the natural thing to do is to let agents vote over outcomes. That is, they tell us which outcomes they like and which they like less. And then we need to make a decision. And we want to be fair in the sense that every agent has equal influence on the outcome. Now, this is actually not so easy to do usually because there are not that many degrees of freedom in the decision we are making, and there are perhaps many, many voters. So we cannot actually guarantee that any single voter has a positive influence on the outcome. So it's a bit tricky to define, but one thing you can say is that a group of voters together, once it's large enough to actually, so that we can guarantee them to have an influence on the outcome, then they should have an influence on the outcome. And that should be equal in the sense that it's proportional to the size of the group. So that's the idea of proportionality. Okay, I'm going to start with a little trick in case you've not seen it before, which is sort of a general way to do fairness in group decision making. And that's just useful to have in mind. And it goes back to John Nash, who is known to many of you from Nash equilibrium. But he did some other things, including on bargaining theory, and that's where this trick comes from. So suppose in the most general model, we have a set of possible outcomes. These could be allocation decisions. So who gets what item, or it could be in participatory budgeting, what things we decide to purchase. So this is perhaps a big set, and then we have a set of agents also, and each agent has a utility value for every outcome. And then if you want to make a group decision, your first idea might be to select the outcome that maximizes the sum of utilities. This is often called utilitarianism or maximizing social welfare. But I'm going to suggest that you should instead select the outcome X that maximizes the product of utilities rather than the sum of utilities. And why might this be a good idea? So there are two intuitions. If we do it with this objective function, then if we rescale some agents' utilities, so for example, for one of the agents, we just double all the utility values here, then the outcome doesn't change. Right? Because it just means that for every X, we have a factor of 2 that we can pull out of the product. And so the optimum X does not change. And so this makes sense because there isn't really a common utility scale. It's not clear what are the units of different people's utilities for different outcomes. So it's good for our decision procedure to be independent of that. If you take instead the thing that maximizes the sum, and some agent multiplies all their utilities by 1,000, then suddenly they become much more important in your decision-making procedure. Whereas here, this does not have an influence. Another intuition is that we impose diminishing marginal utilities. So maximizing the product is the same as maximizing the sum of the logarithm of the utilities. Right, and so we transform agents' utilities with the logarithm. So this means at low utilities, agents are very important because a small increase in utility gives us a high increase in the objective function. But once they're satisfied, it's not very important anymore that we make them even happier. This is another reason why this is fair. And you can often prove in various specific cases, so when this set A here has more structure, that this leads to a formally fair outcome. And so in several of these splitted applications here, what's actually going on is that the people give you their utilities and then they just feed it to Nash and tell you what is the best outcome according to this objective function. Okay, I just wanted to mention this as a sort of general tool to get fairness, and we'll see it appear soon again. Okay, so let's move to the subject of the talk, participatory budgeting. And I've mentioned before, this is where the city government allows its residents to vote over how the budget is spent. So many French cities, and in fact cities around the world, do this now, so you might even have participated in this, but if you haven't, this is roughly what's going on. So you're going to vote, often online, but also on paper. The city tells you what budget, usually tax income, the city has set aside for this participatory budgeting project. So suppose here it's 3 million euros. And then they tell you that you're allowed to approve up to, say, 4 projects. And there's a list of projects that have been proposed, for example, by the residents or by politicians, and they each come with a cost. So for example, the public library might be extended for a cost of 200,000, might add solar panels or bicycle racks on a street, etc. And these all have different costs, and you can vote for things that you think are a good idea. So that's the idea. And then based on these votes, we have to decide which collection of projects to fund, and this is our budget constraint. All right, let me go through an example. No, let me first have another slide about participatory budgeting now being used in hundreds of cities. The largest, I believe, is in Paris for 100 million euros per year. Because this is now used all over the place, if we can find better solutions and can convince politicians to use them, this could improve practice around the world. So this is why this is of interest. Another ways of interest is that the same or similar models are also useful for other things, in particular research grant funding, which is very similar. So you're a grant agency, you have a certain amount of money that you can spend on projects, you get lots of grant proposals in, and you have a committee that needs to decide what to fund, and they face a similar problem where they have different project proposals that come with costs subject to a knapsack constraint, and different experts have different preferences and ideas what are the best projects. Okay, so I've made this fictional city called Circleville, and they are doing a participatory budgeting run this year. So to make things simple, suppose there are 400,000 people who live in Circleville and they have 400,000 euros available to be spent. And Circleville comes in 4 districts, north side, east side, south side, and west side. They all have roughly 100,000 residents, but north side is slightly bigger than the others. Right, and each of these letters here refers to a project together with its cost. Okay, and suppose to keep things simple, that everyone votes exactly for the projects that are in their district. So every person in north side votes for A, B, C, and D, but no other projects. Right, if this is what happens, then once we count the votes, this is the result. These are the projects, these are the votes, and we can see that A, B, C, and D are the most popular. They got the most votes. No surprise, because they are the projects in the largest district. So the standard voting rule, what would it do with this information? Well, it will start filling the knapsack greedily. So it will start with the most popular projects. So these are A, B, C, and D, and it will select some of them, for example, A, B, and D. And now it has spent $380,000 of the available $400,000. So it still has some money left over. So we can go down further in the list. And for example, we can still afford F and I. And now we've spent a total of $394,000 and nothing else is affordable anymore. So the rule now stops. This is its decision. Now, question is this a good rule? And it doesn't really look like it, because we've spent essentially all the money just on projects in north side, and almost 3/4 of the population, we spent very little. I mean, we spent like $14,000 here in east side, but nothing in south side and west side. Right, but presumably these people have paid taxes. They deserve some money to be spent there. So this seems like a bad rule. Rather, we want that everyone gets a reasonable amount spent on projects that they like. Okay, so what can we do? This is a pretty obvious problem. So cities don't do it exactly like I said now. What they usually do is they split their city in parts into the districts, and then each district does a completely separate election from the others. So there would just be a north side election. North side gets $120,000 and they do their own thing with no regard to anything else that happens. So this is very common. In Paris, it would be 16 elections plus one common election also. And that would be the hope that this at least gets rid of these geographical points where north side can dominate everyone else. But the question is this the right way to go about it? And I don't really think so. Why? Well, look at a project like for example, A and T here. A and T are very close to the border between two districts. So it might well be that people living in this area would also vote for T, and people living in this area would also vote for A. But if we do separate elections for each district, they cannot vote for each other. Right? Only North-siders are allowed to vote for A. And so even if a project is near a border, it might be very popular, but the voting rule can't know this because it just doesn't get the right information. Or similarly, C here, C is clearly in some park. It might be building a playground. And so parents from across Circleville might be interested in this project. But with these separate elections, again, only North-siders can vote for C. And so C might look not so popular, and it's extremely expensive, so it will not be selected. Okay, so here is one possible solution that we've recently proposed. So we allow everyone to vote for everything, right? So you're allowed to vote for projects that are not in your own district. But we will first do for each district a virtual district only election, right? So for example, North Side gets 120,000. We take only into account the preferences submitted by the North-siders and then see what is the best thing they can do. So we calculate the maximum welfare solution that can be attained by North-siders with their own budget, which could include projects from elsewhere, if many of them like them. And we do this for each district. So for each district, we know what they do on their own. And then we say a district fair outcome for the citywide election must give each district a welfare of at least what they would have received on their own. And so the idea is that this is an improvement on actually separate elections, because we only do virtual elections. This is a lower bound, but we actually run a citywide election where we can maximize other things and get an efficient outcome that is at least as fair and at least as good for each district as if we had separate elections. I'm just looking through the questions. Yeah, this is all good. So this is one possibility. Unfortunately, it's NP complete to find the best district fair outcome. We found some ways to speed this up if you're allowing some randomizations or if you're allowed to approximate. This number here is 1/e. But so this is one way you can go about it, and it's nice because it kind of improves on the status quo directly. But it's not clear that this is the optimum way of going about it, and rather we might want to be fair to all interest groups, not just predefined districts. So the previous slides method still takes districts as the important building blocks. But it might be that there are other groups that we need to be fair to, such as people living in this corner of Circleville, or people interested in parks, or maybe people who want these projects to be built because it might be a bicycle path along the river. And so bicyclists from all across the city are in favor of it. Right. So how can we be fair to all these interest groups? And typically we won't be given them. So the nice thing with districts is we know them. Right, so people log in and they say where they live, and then we know these, and we know which groups we need to be fair to. But how can we be fair to all interest groups? So the voting rule will need to figure out what are these groups that we need to be fair to. And this is what I mean by proportionally representative participatory budgeting. because we need to be representative for everyone, and the representation needs to be proportional to the size of interest groups. Good, so how can we do this? This seems like a difficult task to be fair to everyone simultaneously. And so let's go to an easier domain. So here's another way of phrasing it. So proportional representation requires that a group of 30% of the voters, for example, if they have similar interests, then they should be represented by spending of about 30% of the budget. So 30% of the voters becomes 30% of the budget. And crucially, the same voter could be part of several interest groups. So that's different from the districts where each voter is just part of one group. Here it could be part of many different groups. Okay, so now let's talk about multi-winner voting. Suppose our budget is, say, 577 euros, and each project costs €1. Then we are in a special case that looks like a parliament election, right? So each seat in the parliament is one of the projects. Voters can vote over which people they want to fill those seats, right? And we have at most, say, 577 seats available. Right, this is called the unit cost assumption because each project costs the same. And that gets us into this realm of multi-winner voting, where proportionality is much better understood because, of course, proportional representation in parliament elections is an important thing. So I guess for the size 577, you guys don't do very much proportionality as far as I know, but the Swedes do. And so they have some ideas from 100 years ago. Let me go through some formal definitions of proportionality so we can compare them. For easy annotation, assume that there are exactly 100 seats. So this is K is 100 euros and everything costs €1, or K equals 100 seats. And suppose S is a group of voters. So this means any subset of voters. And then these are 4 different fairness notions that I've denoted here by different stars. So star system, 1 star is the weakest, up to 4 stars the strongest. So this simplest notion says that if this group of voters consists of 30% of the voters and they all vote for the same 30 candidates. So note, I'm now taking away this restriction that you're allowed to vote for at most, say, 4 candidates. I don't care about for how many you vote, any number. Then at least 30 seats are filled with candidates they approve. So they might vote for more than 30 candidates, but 30 of them should be selected. So this is a group of voters that have the exact same preferences. And so then we should represent them proportionally to their size. So of course, 30 is just one value and it's supposed to hold for all possible percentages. PGAR allows them to have slightly different preferences. So again, we have a group of 30% of voters, and there are at least 30 candidates that they all approve. Then at most 70 seats are filled with candidates that none of them approve. Or in other words, at least 30 seats are filled with candidates that at least one person in the group approves. And then we can go even stronger and even stronger. So in the core, it says if we have a group of 30% of voters, and suppose they can find some set T of 30 candidates, then to satisfy the core, at least one member of S must prefer the outcome we've selected to T. So it's not allowed that a group of 30% of voters can find something that they all prefer to the outcome. Because if they can find such a thing, then they are not well represented. That's the idea. Okay. So with these notions in mind, what can we do? Here are 3 different multi-winner voting rules that have been proposed over time. There's the simplest rule, the utilitarian rule, and it's just essentially the naive rule we've seen before, which just selects the K candidates who have been approved most often. Right? This is a nice rule. It's very quick to compute. But it's not at all proportional. It's 0 stars. It doesn't even satisfy the weakest version. Why not? Well, it's easy to see if you have a majority of people, 51%, who all have the same preferences, then they can decide everyone in the committee. And even if 49% the others have the same preferences, we will give them 0 of the seats. because none of their candidates sort of get into the highest approval scores territory. And there is Thiele's method, proposed in 1895 in the context of Sweden, who were looking for a new method to elect their parliaments. And that method finds a committee that maximizes this magic function here. It's a sum over voters. And then it's this utility score here, 1 plus a half plus a third plus ... plus 1 over the number of committee members that voter I approves. This might look kind of weird. Turns out this is the best function to use here. And an intuition for why this is right is that this is very similar to maximizing the product of utilities that we've seen before, because these harmonic numbers here approximate the logarithm. But this is the right way to do it for this discrete case. So you don't want to actually do exact Nash or the exact logarithm. That doesn't quite get the rounding right, but this function. And this is actually very proportional. It's 3 out of 4 stars in proportionality. It comes at the cost of being NP complete to compute. But in my experience, there's an easy integer linear programming formulation that does it in reasonable time. It's actually an open problem whether this 4-star proportionality, which is this core that I was talking about, always exists. So on all instances that people have tried, there always exists at least one outcome, but all the voting rules that have been proposed over time, there are examples where we know that they fail 4-star proportionality. So 3-star proportionality is the best we know. And then there's a different method proposed 1894, 1 year before Thiele's method, and they had kind of fight in the literature who had the better rule. And the idea here is, talking very abstractly, voters can sequentially purchase K candidates using virtual money, and voters will only pay for candidates that they approve. This is polynomial time in contrast to this complicated method, and it's almost as proportional 2-star proportionality. And we've argued in a recent paper that it's actually, this understates it, and it's actually slightly better than that. And so this contrast here between NP completeness and polynomial time is part of the conflict between these two, because which is the easier rule to do. This one's easier to compute, right, formally speaking, but this one's easier to understand. Like this is quite complicated, and so I've not even given you the definition of the rule, whereas this just fits on a very small slide. Okay, let me briefly talk about the second row of axioms here, just about strategy proofness and manipulability. So the question is, do you always want to tell the voting method your true preferences? Or is it sometimes better for you to lie and to misrepresent your preferences and vote for things that you don't actually like, in the hope that the voting rule will thereby actually select something that's better for you? And for the utilitarian rule, it's quite easy to see that you don't want to do that. But unfortunately, for Thiele's method and Fragment's method, sometimes it is better for you to not be completely forthcoming with what you really think. So let's go through a brief example where we have 5 voters. The first 3 voters, they like candidates A, B, and C. And voters 4 and 5, they like candidates A, B, and D. And in this example, actually, all the 3 rules make the same decision. Let's select A, B, and C. And this makes some sense. So A and B are clearly very strong candidates. So there are 3 seats. A and B are strong candidates, so unanimously approved. We probably want to select them. And then we still have 1 seat left to fill. We can either choose C or D, and C is better than D. So everyone does that. Okay, so now suppose voter 5 gets clever and pretends not to actually like A and B. So voter 5 only votes for D now and says, I don't like A and B. This utilitarian rule that just maximizes social welfare, the sum of utilities, is unfazed, still selects A, B, and C. Why is that? Well, A is approved by 4 people, B is approved by 4 people, then C is approved by 3 people, and D by 2. And so the 3 most popular are A, B, and C. But these proportional rules, these fair rules, they kind of feel sorry for voter 5. Because if you were to select A, B, and C, then voter 5 gets no one that they like. And because voter 5 only likes D. And so therefore, they then select D here. Now, and this seems like quite a general thing that fair voting rules will do. If you pretend to be unhappy with sort of the general preferences or the general outcome, then the fair voting rule will feel sorry for you and will try to make you happier. And thereby, in this kind of way, you can pull the voting outcome towards you. So there's a natural question: is there a multi-winner voting rule that is proportional, even just in the weakest sense, but that cannot be manipulated by this strategy? Right, and if you look at these here, doesn't look like it, because all the ones that have a check mark in the third row don't work out in the second row. And we can actually answer this question using set solving. So if we are too lazy to think about it, and it's actually quite complicated, then we can just write down a conjunctive normal form formula for the question: is there a voting rule that is proportional but not manipulable? And so the way it works is we generate a variable for all possible input profiles P. And for each of these profiles of possible preferences that we could see, we generate all allowed outputs W. So by allowed, I mean proportional, say in the 1-star sense. And then we introduce a variable that says at input P, we give output W. And then we put in some simple constraints. These constraints say at each input, we output exactly one of the allowed Ws. And constraint 2 prohibits manipulations. Right, so it goes through all possible profiles and all profiles P dash that we can obtain from P by just changing one voter's input. And then we say that if in the truthful profile, we have W as the outcome, then it can't be the case that at the manipulated profile, we select a different outcome that the manipulator prefers to the original outcome. This is a massive formula because there are exponentially many input profiles. But if we fix the number of voters, the number of candidates, and the size of the committee to small values, then we can write this down and we can ask a set solver what's the answer. And if it says, yes, it's satisfiable, then we found a good voting rule that we can then analyze and maybe get some ideas from. It won't be so easy because it's a lookup table, right? It's just a list of all possible inputs and what the output is that you select there. And I've never had any success decoding the output in a satisfiable case. Or I get more excited if it says unsatisfiable, because then we found an impossibility theorem and you can publish a paper, especially because you can, in these cases, quite easily get a proof of the impossibility theorem using minimal unsatisfiable sets, MUSs. And so an MUS is just a selection of these constraints, a subset that is already unsatisfiable. It's minimal, so that if you take any of these constraints out, then the rest can be satisfied. And so an MUS just gives you a soup of proof steps, and it tells you these proof steps are enough to prove this impossibility theorem. And for these voting formulas, these MUSs turn out to be remarkably small, like maybe 50 different constraints. And so it's then possible to piece them together. In fact, so let's think about this. The main constraint is these manipulation constraints. And what they do is they link two different profiles together, right? What happens at profile P together with what happens at this manipulated profile P dash. And so this MUS, you can draw it as a graph like this. So each node here is one of the profiles, and they are connected by an edge if there's a constraint in your MUS that links them, right? And then you can look at your proof and try to make sense of it. And that's not so easy, but at some point, then you figure out what are the important ones, and you find some symmetric profiles. And then with these symmetric profiles, you can add some symmetry breaking constraints. And then you get a different MUS that looks like this, is slightly more approachable. You can figure out that these these little tails coming out of some of the profiles here is just the same thing again and again and again. So you can put this as a kind of lemma also into your SAT formula, and then you get this. And this is actually easy. So what this does is just you start here. You have two possible choices there. You without orthogonality, you go left and you go loop, and then at the end you arrive at a contradiction, and that's your proof. And then you can write it down, and it's a human readable proof that's found by a SAT solver. And that kind of strategy actually works for many of these voting type problems where you're looking for a rule that satisfies several axioms. Okay, so let's, after this excursion into multi-winner voting, let's get back to budgeting. Let me briefly say, given this impossibility that we've now seen between proportionality and manipulation, it means that any proportional rule we find for participatory budgeting must also be manipulable in this kind of way where you pretend not to like popular projects. Why? Because, of course, these parliament elections are a special case of participatory budgeting. Okay, anyway, we want to be proportional, so what can we do? The first idea is to use this Thiele method and to calculate the outcome that is optimal on this objective function with lots of fractions, which is similar to multiplying utilities. And unfortunately, while I was advocating for you to use this everywhere, for participatory budgeting, it doesn't actually work. Here's an example. Not circleable, but a bit smaller. This is one town. One town has 90,000 people and 90,000 euros available for budgeting. It has two districts, left side and right side, 60,000 people and 30,000 people. And there are three projects in left side. Say they are all, like everyone in left side approves L1, L2, and L3, and everyone in right side approves R. Now, given these prices and the available budget, what can you do? You can either afford to do all the L projects that cost 60,000, and once you've done that, you cannot afford the R project anymore. Or you can afford to do two of the L projects and the R project. And then you can calculate the PAV scores. PAV is another name for Thiele's method, and it thinks that doing R is a good idea. So you do two L's and one R. But that's the wrong outcome. Why? Because left side deserves $60,000. Right? That's their proportional share of the budget. And so they should be able to spend it on projects that they like, and they can afford all the 3L projects. So the proportional outcome would have them spend it on their projects. And right side is just unlucky. The only idea that they've come up with is something that is just way too much for their size. Okay, but maybe this is not exactly the right score to use. Maybe we should use some other objective function, but that won't work either. So let's have a look at two town. Two town is very similar to one town, has the same districts, but now the prices have changed. So now the L projects are all costing 30,000, and the R project is also costing 30,000. Now we still have the same choices as before. So we can either afford all the L's, which costs 90,000, or we can afford two L's and one R, which also costs 90,000. Noticeably, the PAV scores haven't changed, but the outcome here, the right outcome has changed, because now it's not allowed to do all the 3L projects, because right side over here, they deserve $30,000 worth of spending, so they deserve to have their R project implemented, right? But notice, so these two instances are extremely similar. They have the same budget, the same population, the same district structure, the same utilities, the same people vote for the same projects in both cases. We have the same feasible sets. Everything's the same. The only thing that's different is the prices. And in these two extremely similar instances, the correct choice, if you want to be proportional, differs. So any rule that actually works needs to make use of additional information that's not in this list. That is, it needs to make use of information of the prices of the projects, not just the feasible sets. And so any rule that just maximizes something over the collection of feasible sets won't work. Okay, so we need a different rule. Yeah, here's that is the theorem statement. So every voting rule that only depends essentially on the feasible sets and the utilities won't work. So here is our own proposal. Unfortunately, we are not very creative with names, so we called it Rule X. And kind of now it's too late because other people have cited it with this name, so it's sticking. But we couldn't think of something else. So here's the idea. It's actually quite simple. Let's take the budget that's available and split it evenly among all the voters. Right, so each person gets their share of the budget. We put it into a virtual bank account. And then repeatedly until the budget runs out, we identify a project whose supporters, that is the voters who have supported and approved that project, have enough money left to afford it in their bank accounts. We find such a project, and then we implement it, and we charge the voters who voted for it the cost of that project. Right, and we do this as evenly as possible. So we split the cost of the project as evenly as possible among supporters and charge them, and we repeat until the budget runs out or nothing is affordable anymore. Okay, so let's think briefly about this as evenly as possible. What does that mean? And also in particular, let's think about, suppose there are several projects that are affordable. That will be the case, especially at the start of the rule. Then how do we choose between several affordable projects? The answer is we're going to take the project where the maximum payment is smallest. So for each project, we try to, as evenly as possible, spread the cost, and we look at what is the maximum any single voter would be asked to pay for it. And we take the one where this value is smallest. The reason we do it is that this has three nice properties. It means if a project is cheaper than another, but everything else is the same, then that's better. So we prefer cheaper to more expensive projects if the same voters are satisfied by it. If you have wealthier supporters, that's better. We are more likely to select your project. Why is that the right idea? Because wealthy is bad. If a voter has lots of money in their bank account, it means that we didn't do things so far that they like. So they've been underserved, right? So if you're wealthy, we better do something for you, better select something that you voted for. And more supporters is better. So if you have more supporters, we can spread the cost of the project more evenly. So here are some examples. Suppose we have two projects. They are liked by the same voters, namely voters 1 through 5. That's possibly also voter 6, but voter 6 has already spent all their money, right? So they are the same, except that project 2 costs less, right? So project 1 costs $16. We spread the amount as evenly as possible. So voters 1 and 2 spend all their money. Voters 3, 4, and 5 all spend $4. And so this amount sums up to 16. Here's the same kind of project, the same people who like it, but now the cost is only $9 and we can spread it like this, right? And then project 2 is better than project 1 because the maximum payment is only $2 rather than $4. And so we take project 2 rather than project 1. And here's another comparison. This time around, the supporters of project 2, so project 1 and 2 now cost the same, both $16, but now the supporters of project 2 are wealthier. That means that we can spread the cost of $16 more evenly at $2.66 each person, whereas here we needed $4 because voters 1, 2, and 6 here don't have much money left. So that's the idea. And if we do this, then we get the analog of 3-star proportionality. And there the idea was if we have a group of voters, they approve at least L projects in common. These L projects cost at most an S/N fraction of the budget, so they can afford it given their size. Then at least one voter in S needs to approve at least L candidates in the selected outcome. It's slightly difficult to understand, but roughly the idea is each group of voters, if they have similar enough preferences, that they can afford with their size, then we can't ignore them. We need to make at least one person in that group happy. And rule X satisfies this notion. And the proof strategy is roughly speaking that if you have such a group who have such similar preferences, then rule X will actually spend their money. It will take most of their money, and thereby that means it must make them happy, because spending money makes you happy in this rule. Okay, we can extend this slightly. So at the moment, we are only doing this approval idea, so where you approve several candidates, but it's not clear that for participatory budgeting, this is the right thing to do. Here's an example taken from the Paris election in the 16th arrondissement, where I'll be working shortly. They had, among the projects that were available, was one that was refurbish a sports facility, tennis courts, etc. It was very expensive at 560,000 euros, and it got 775 votes. And then there was another project where one of the schools wanted some materials for a classroom project. I think they wanted to build their own board game or something in class. And so needed some paper and some scissors and things like this, and maybe some plastic chips, and it costed 3,000 euros. And it got 670 votes. So you can see what will happen actually using the naive voting rule that is used. The sports facility is built, because it has more votes than the classroom project. So the classroom project can't be done anymore because we spent all our money on the tennis courts. And so 3,000 euros isn't available anymore. So this is what happened. But more broadly, it seems like the idea of just voting for something or not voting for something doesn't really capture it. Right? You have a project that is 15% more popular, but it costs 186 times as much. You really want to ask people, is it worth the money? Like, do you like it enough that it's worth the money? And so we want to probably replace 0, 1 by actual numbers, and that people put in numbers. And if you do that, you can still use rule X. It still satisfies EJR, roughly speaking. And so our rule can accommodate this more general input also. By the way, we also have a rule that satisfies even stronger guarantees than rule X, but it's extremely hard to compute. I tried it on data from Warsaw, and I took the smallest district with just 1,000 voters, and I gave up after 4 hours because it didn't make any progress. So yeah, this is where we are stuck at the moment. Okay, so I'm pretty much done. Just as some general discussion points, this idea of proportionality and fairness can be applied to budgeting, or it can be applied to all kinds of decision-making situations, such as scheduling, designing things together, making recommendations to a group, etc. And all over the place, you can use this idea of proportionality where everyone has the same amount of influence, at least once they pool their influence into a group. And you can, if you have some kind of optimization problem, you can try to inject proportionality into it. Another question is whether we can implement sophisticated voting rules, such as the one rule X that I talked about, in public applications, or are these just too complicated? If they are too complicated, can we find rules that are just much simpler, but are still formally okay in some way or other? And what about computational complexity? If you have a difficult rule, can we actually use it in public applications or not? If your rule will just take 5 days on the most expensive server in Amazon's warehouse, is that okay? Even if we don't have a guarantee that it will actually find the optimum or not. And another one is fairness over time. So I've only talked about a single vote, but participatory budgeting typically happens every year. And so maybe we want to look at the situation over time, which would, for example, mean if some district got too little money in 1 year, then we keep that in mind, we memorize that, and in future years, we give them more money. And it's the same happens all over the place, or is applicable everywhere, where we want to be fair over time. What does that mean, and what's the right way of doing it? All right, thanks for your attention, and I'm happy to answer any questions.
Thank you very much, Dominik. Thank you for your very clear and inspiring presentation. I'm sure that it can generate many questions, many new problems or research directions. So I ask the attendees if they have a new question. Yes.